Welcome back, guys. This is probably going to be your favorite lesson of the whole semester. We're doing distance, rate, and time application word problems. No, I'm kind of kidding. These are the problems that honestly give math like maybe a bad name. Like you've probably heard of these types of problems. It's like a train leaves at this time, and then a couple hours later, another train leaves going faster. How long is it going to take for them to catch up? Like for real, I've heard of these math problems being made fun of in movies before. They're a little challenging, but if we take it step by step and kind of organize the information just right, then they're pretty manageable. So that's what I'm going to try to help you out with here. Obviously, we're going to take a lot of time to practice these because they are kind of challenging. So we'll give ourselves a couple days to learn it. So let's just introduce it and give a couple examples today to start off these distance, rate, time application problems. Now, if you're thinking about how you find an object's distance that's traveled, to do that, and you guys know how to do that, maybe you just have never set it up like this, but to find how far something travels, you can multiply its rate and its time. Okay, now rate just, that's the same thing as speed. So I'm going to make like a note there. That just equals how fast something's going. So, okay, simple example. Think if you're driving. And again, you guys could figure this out. If you're traveling 40 miles an hour, if that's your speed, and you go that fast, so you're on cruise control, you go that fast for 3 hours, that's a time. You guys could figure out how many miles you would cover. Well, you're going 40 miles per hour, 40 miles every hour, and you're traveling for 3 hours. So you would just do 40 times 3. It's not very fast. So you wouldn't travel as far as you would if you were going like 70 miles an hour, but 40 times 3, you would go 120 miles in those 3 hours at that speed. Okay, so again, I think you could figure that out, but general purposes, and I'm going to write a little note off to the side. To figure out an object's distance, you just do rate times time. Now, we're going to call these distance problems dirt problems. And it's kind of in the title here. No, there's not an I, but we just call these dirt. So if you hear me say, oh, dirt problems, that's what I'm talking about. If you just do speed times time, that gives you your distance. Okay, so yay, that's what we're doing today. Now, there's two types of examples that you're going to see. Okay, so the problems here are either going to be one of these two types. They're either going to be same direction travel, which means that two objects like two trains, two planes, they're covering the same distance, so their distances are equal. Or the two objects are going to be traveling in opposite directions. They're going to be going away from each other. When this happens, the distances, they're not equal. You have to add them together to kind of work out whatever it is you're trying to find. Okay, so these are good notes to make. The problems are either one of these two types of things. And in the problem, they'll mention what type it is, and that will help you set up your equation, which we all know is the hard part. So I'm just going to do one of each example, but again, we're going to practice these together for a couple days here. So let's just introduce it, show you one example of each, and then we'll get to practice later, which is really where you're going to get comfortable with these problems on your own. Okay, so first step is to read it, and I wrote the steps out nice on this first example. Step 1, as you're reading it, it's always important to underline the key information. So I'm looking at a train leaves a station at 1 p.m. Okay, time might be important here. So a train leaves the station at 1 p.m. and it's traveling at an average speed of 60 miles an hour. All numbers, always important. Okay, a high-speed train, so obviously this one's going to be going a little bit faster, it leaves the same station 2 hours later, traveling 20 miles an hour faster than the first train. So it leaves later, but it's going faster. The second train follows the same route as the first train on a parallel track. Okay, so this is them just trying to point out to me that these trains are going in the same direction. They're not going to run into each other because they're on parallel tracks. Okay, but they are taking the same route, so they're going the same direction. That would just clue me into, okay, I'm looking at this first type of example. I want to know in how many hours will the second train catch up with the first? Okay, so I underlined important information. I read it. Now I need to define my variable. This is the same kind of step that we were looking at with our previous word problems this unit. Now, before we look at like this crazy table and everything, I want you to be aware that the variable on these problems is either going to be the rate or the time. Okay, it's going to be one or the other on these problems. So I'm going to make a note of that. It's going to be either rate or time. So you're either going to use R or T. That's my suggestion. So if I want to know, and you look to the question to define the variable, in how many hours? So I want to know after 3 hours, after 5 hours. I want to know how many hours are they going to catch up with each other. So I don't know the time on this one, so I'm going to say T equals time. Trying to figure out the time, the hours, so that's going to be my variable. Now, there's this table that's going on here, and I'm going to provide you with the table as we get started, but when we get a little bit better at these, you're going to have to make the table on your own. Okay, but we'll take it slow. So I've got the table filled out. We just need to fill in the information. So over here, this is a typo. Clearly, this was not changed from a different example, but cross off airplane and jet. I'm not talking about an airplane and a jet. I'm talking about two different trains. So I'm just going to say train 1, train 2. So off to the left in your table, you always put like the two things that you're talking about. Got two different trains. I know that rate just means speed. So I'm going to try to fill in their speeds, fill in the times, and once I've got the rate and the time figured out, I know that rate times time, what I said here, is going to give me my distance. So the distance is easy once you can fill in the rates and the times. So let's see if we can do that. So rate just means speed. I know the first train, they told me it was going 60 miles an hour. So they kind of gave me that real clearly there. The high-speed train leaves 2 hours later. That'll come into play in a minute. It was going 20 miles an hour faster. Okay, well, if the first train was going 60, 20 miles an hour faster than that would be 80. Okay, so the speed's not too terrible to fill out on this problem. The time is maybe what's going to be the challenging part, and that's where T is going to come in. So let me use my lovely art skills to draw a picture here. And in class, you guys, I'm going to give you, like, we're going to do a little demonstration, I guess, of these problems, and maybe getting the visual in real life will help you understand these a little bit more. Like I said, these are challenging, so it takes practice. It's probably not just going to automatically click after one example, so don't put that pressure on yourself. But here's the train station. I know, beautiful picture. We got one train, and then we got a high-speed train. So that one's longer with more wheels, so that goes faster. My art skills are terrible, don't judge. All right, so here's the situation. They're both at the same station. One of them leaves, the one that's going slower. So it leaves, there it goes. It's going 60 miles an hour. 2 hours later, so I don't know how many hours this train travels. All I know is that 2 hours later, the second one leaves. Okay, so after 2 hours, this one leaves. They're on parallel tracks. They're going in the same direction. So this is kind of all I know so far. Here's how you fill in the time. Like I said, I don't know how long these trains were traveling for. They didn't tell me that. So all I'm going to do is call the first train's time. I'm going to call it T because I don't know that, so I'm going to give it the variable. Now, I do have to factor in the fact that the second train left 2 hours later. That's important. That needs to come into play in your table. So first train leaves. Second train is just kind of like hanging out. People are getting snacks. The conductor's doing whatever he wants. 2 hours later, that one leaves. So there's 2 hours that the first train's traveling that the second train is not. It's just hanging out at the station. So however long the first train travels, the second train basically travels 2 hours less than that because it didn't travel for those first 2 hours. So I'm going to take the first train's time and subtract 2 since it left 2 hours later. And I'm going to call its time t minus 2. Anytime you see a situation like that where it's like it left an hour later, 3 hours later, you always do that. T minus however many hours for the second train. And that's the tricky part. That is the part that takes practice. Write it. We're going to practice it, though, to kind of get that down a little bit better. Like I said, once you have the rate and time filled in, distance shouldn't be that bad because you just multiply across. That's kind of why we make the table and organize it this way. I know to get how far something traveled, what distance was covered here, I just do its speed times its time. So for the distance on the first train, I just do 60 times t, which I'm going to just write as 60t. For train 2, just like in proportions, you have to put parentheses around addition or subtraction problems. So I'm going to do 80 times t minus 2 when I multiply across there. Okay, so once I've got the table filled out, I need to write an equation. I need to set something up with an equal sign so I can solve this for t to answer the question. How many hours? So notice how time is figured. It's the time spent traveling for each train. I don't know how long each train was traveling. That's what I want to figure out. But since we know that the trains covered equal distances, we can set up an equation using the expressions that represent each train's distance. So look at your table. Here's where the distances are. Okay, so it means nothing to me, but this train traveled 60t. This train traveled 80 minus t minus 2, or 80 times t minus 2. They are traveling the same distance because eventually, this train's going faster, so eventually they're going to meet up at the same spot. And I want to know how long did it take for them to meet at this same spot. So here's what I'm going to do. They're traveling the exact same distance. This one went this far, this one went this far. So I'm going to take their distances and I'm going to set them equal. Okay, so just take those distance expressions, set them equal. You always do that for same direction problems. You set their different distances equal. This should be fairly easy at this point. Once it's set up, all you got to do is distribute and solve this for t, which I'm confident that all of you guys can do this from here. Okay, so I'm going to bring, and be careful here, I'm going to bring the smaller t's by subtracting the 60 over to the other side. Now what I've done is now I have 0 on this side, on the left side, so keep it straight here. And then maybe I'm weird by doing this, but then I'm going to add 160. So I have 160 equals 20t. You can use your calculators. I ran out of room, but we should all know that now I divide by 20. So it's just 8 for t. Okay, so what does that mean then exactly? Well, that means that the time for the first train was 8 hours. The second train was that time minus 2, so that train traveled 6 hours. I want to know how long did it take the second train to catch up with the first. That's what the original question asked. Okay, so think about it. Answer the right question. You always have to make sure you answer the question. I want to know the second train, how long did it take? Well, the first train just traveled t, which was 8. This train traveled 8 minus 2, so it actually only traveled 6 hours. So it took the second train 6 hours to catch up with the first train. And if I want to figure out what time they actually caught up with each other, come back to the question. The first train left at 1 p.m. So if it traveled for 8 hours, and I know the second train would have left at 3, if it traveled for 8 hours, well, 8 hours after 1 o'clock would be 9 p.m. Yay, wasn't that fun? Okay, I'm kidding. These are like seriously a lot of work. Again, it just takes practice. So that's an example of a same direction problem. Let's flip it over and do an opposite direction, and then we've got both types covered. and it'll just be practice from here on out. So let's read it, and we'll do a little visual again in class next time I see you to kind of help with this. But it says 2 jets leave Dallas at the same time and fly in opposite directions. Okay, right there. That flat out tells me this is an opposite direction problem. They always are set up the same. This will be helpful in the future. So one jet is flying west, 50 miles an hour faster than the other. After 2 hours, the jets are 2,500 miles apart. I want to find the speed of each jet. Okay, so we underlined, we read. I told you that the variable is either going to be rate or time. So think about what we're trying to figure out on this one. Look at the last sentence. I want to find the speed of each jet. Remember, speed is the same thing as rate. You can use S, but I mean, I would use RRT just on all of these. Figure out which one you're trying to find, use that letter. So I don't know the speed, so I'm going to say R equals rate. Trying to figure that out. I'm going to make a table next. I'm going to organize all the information, fill in what you're talking about. I'm talking about a west flying jet, and obviously the other one's going east. You could put jet 1, jet 2. Kind of helps though to do the west thing since they were specific about how fast that one was going. Okay, here's my little visual for you. Dallas Airport. So we got one jet. Oh my gosh, I cannot draw a plane. It's like really good. Looks like a bug. You can make fun of me next time you see me. Okay, so I've got 2 jets at the Dallas airport. They're flying away from each other, so they're not traveling the same direction anymore. So one, let's see if I do my little compass, north, south, east, west. So one's going west, and it's going 50 miles an hour faster than the other. So this one's going east. Now, after 2 hours, so exactly 2 hours later, we'll say, meh, stop the time. This one's going to land, or it's going to be here. This one's going to be here after 2 hours. And obviously think about it. They don't cover the same distance because one's going faster. If I'm going faster, I'm going to cover more distance in 2 hours. So the west flying jet is going to go further than the east flying jet. But they did tell me after 2 hours, they're 2,500 miles apart. So this distance from here to here is 2,500 miles apart. Okay, so let's see if we can fill this table out. So the speeds, all I know is that the one going west is going 50 miles an hour faster. So let's call the one going east just plain R. I know that the west one's going 50 faster, so I'm going to take that speed and add 50 and call it R plus 50. That's the tricky part. Where the variable is in the table, that's the hard part to fill out. The time on this one's easy. I know they're both traveling for exactly 2 hours. So don't hurt yourself filling that out. Once you have rate and time, you just multiply across to get the distances. Okay, don't forget to use your parentheses around addition or subtraction problems, so you don't forget to distribute. I'm just going to call the east jet's distance 2R. Now, if it's same direction, you just set the distances equal. These are different, and note that there's a number in the problem that I haven't used yet. This will always happen on opposite direction. So since we know that the jets cover different distances, one's going to go further than the other, the one going faster. Here's how we're going to set up our equation to solve. We're going to add the distances and set it equal to that number that we haven't used yet. Okay, so take your distances, here they are. And again, maybe the visual in class or this visual right here is helpful. I know that they're 2,500 miles apart. So if I take how far this one went and add to it how far this one went, that's going to total the distance between them, which is 2,500 miles. So that's what I set this equal to. Again, that's the super hard part, just setting up the equation. I'm confident that you guys can all solve it once it's set up here. So I just distribute. on my line if I need it. Then I'm going to combine like terms, so I'm going to add those r's together. Hopefully from here, this two-step equation is pretty straightforward for all of us. And then my last step, I would just divide by 4. If you need a calculator, use it, but I would get 600. Now, you always have to make sure you answer the question on these problems, and all the problems, okay? So go back up and make sure you're answering the correct question. This one says, find the speed of both jets. Okay, so I got to come back to your table. That's helpful. Look at the speed column. Here it is, the rate. So plane R is 600, so that would be the east jet. 600 plus 50 would be 650 for the west jet. So answer your question carefully. The westbound jet was going 650 miles per hour, and the eastbound jet was going 600 miles per hour. Well, it would be helpful if you could see that. There you go. All right, so that's our dirt problems. More practice to come.